Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing unit number 10, lesson number 7 on solids and their cross sections. So we've only got a few more lessons left in Common Core Geometry and they're all going to be devoted to the three-dimensional world that we live in. And it kind of makes sense, that we've started with real kind of two-dimensional work, right? Flat shapes that sort of live in the plane, if you will. And now we're going to do a few lessons on three-dimensional objects and how they relate to those two-dimensional shapes, specifically what their cross-sections look like. So let's kind of jump into it. Today's lesson, we're going to introduce many of the shapes, all right? And you're going to want to learn this terminology and kind of learn what makes a prism and a cylinder and things like that. But let's jump right into it and talk about prisms, okay? Exercise number 1. A prism is a solid that has two congruent faces, all right? Two congruent faces means that they're identical, those are the bases, with all the other faces being parallelograms. Two examples of right prisms are shown below. Right now, the box is the box. You've seen 1,000,001 boxes, but here's, kind of taking a look at this prism, right? The idea is we've got this pentagon, right? This one looks like a regular pentagon, and an identical one that's sort of parallel to it in three-dimensional space down here. We then connect those vertices, and all of these sides then are parallelograms. All right, these two particular prisms are what are called right prisms. And letter A asks us, why do you believe that they're called right prisms? Why would that be? All right, well, and that's because all of the non-base faces are rectangles. All of the non-base faces are rectangles, right? So, in other words, these lines are coming up directly vertically. They're not tilted in any way from the bases, all right? Simple enough, right? And you see prisms all over the place, especially in terms of kind of like a box like that. Now, let's talk a little bit about cross sections before we even get into the rest of this problem, right? What we're talking about with a cross section is what do we get when we take a three-dimensional solid and we slice it, right? And then we take a look, what kind of a two-dimensional shape are we looking at? That's a cross section, okay? So let's kind of come down to letter B. If you sliced a prism with a horizontal plane, meaning a plane that was parallel to the two bases, right? What would be true about the cross section that you would see? Take a look at this particular one. What's true about this cross section that's outlined? Well, it would be congruent to the two bases, right? It would be congruent . Hey, there's my red. Let me get rid of that red B and put in a blue one. It would be congruent to the two bases. So when I slice a prism horizontally, or when I slice it parallel to the bases, I get slices that are also bases. In other words, are congruent to the bases. The cross section of a prism doesn't change as you slice it horizontally. On the other hand, letter C, if you sliced a prism with a vertical plane, what would be true about the cross section that you would see? So here we've got a nice prism. It's got a triangle here and an identical triangle down there. Again, all the sides then are being connected, or all those vertices are being connected. What would be true about these cross sections? And they would be parallelograms. In the case of right prisms, they would also be rectangles, right? So this one kind of looks rectangular, although it's a little bit hard to tell without being able to kind of rotate physically this shape, all right? But it kind of makes sense. So everything vertically ends up being those parallelograms, and then every kind of horizontal slice ends up being congruent to those bases. All right, so simple enough. Plus it's an awesome word, a prism, right? Now, we've also got cylinders, okay? And cylinders and prisms are essentially the same. The difference between a cylinder and a prism is that with a cylinder, the bases are not polygons, okay? But they are identical shapes. So let's take a look at exercise 2. Exercise number 2. A cylinder is a shape very similar to a prism, except the base face is enclosed by a curve rather than a polygon. Typically, this curve is a circle. The most common is a right circular cylinder. So we've all seen right circular cylinders. In fact, if I just said, hey, I've got a cylinder, pretty much everyone would assume what I was talking about was a right circular cylinder. In other words, a circle up here and a circle down here as a base, and then the lateral face that goes around the cylinder is perpendicular to those two bases, right? Letter A asks us, for a right circular cylinder, the most common and shown, what are the two measurements that control its size? Right? What do you think I would need to know in order to calculate things like the volume or the surface area or what have you for that cylinder? All right. Well, it kind of depends, but certainly the height and either the radius or diameter of the base. More commonly, it's the radius. So the height and the radius of the cylinder. All right, the radius just being the radius of those two circles, and the height being the distance between the two circles. Okay, letter B. What two-dimensional shape wraps around the surface laterally? What are its dimensions? So in other words, if I took, this cylinder, and I kind of took this thing that wraps around it laterally, and I unwrapped it, what would that shape be? It would be a rectangle, right? So literally, if I came up and I made a cut, and I unwrapped that like this, it would be a rectangle, right? And what would its dimensions be? Well, a rectangle normally has a, kind of a width and a height. So you'd have a height. But then you'd also have this width of the rectangle. And what's really cool is the width of the rectangle would equal the circumference of the base, right? It's kind of neat. And that would actually allow you to calculate the area that wraps around this cylinder, because you'd know the height, you would know the radius of the circle, and so as you unwrap it, that length would simply be the circumference of that circle. All right, finally, important, what two-dimensional figure, when rotated about one of its sides, would produce a right circular cylinder? So sometimes you can produce a figure by a three-dimensional figure by rotating a two-dimensional figure around some axis. What would you have to rotate in order to produce a cylinder? You'd have to rotate a rectangle. All right, what two-dimensional figure, when rotated about one of its sides, would produce a right circular cylinder? And that would also be a rectangle. It says, draw the figure on the cylinder above to illustrate. I'm going to just get rid of this for a second. So here's the idea that we're getting at here. All right, let's say that we took a rectangle like this. That doesn't look too much like a rectangle now. Let me kind of maybe go more like this. All right, I'm going to just put an axis like this. If I rotated that rectangle about this axis, it would create that cylinder, right? If I just kind of rotated it around there, it would sweep out everything that that cylinder is occupying, all the three-dimensional space that that cylinder is taking up, I would hit by rotating that rectangle around that axis. Imagine taking a rectangle and just kind of gluing it to this pen and spinning it around. That would create a cylinder. All right, it's kind of cool. All right, let's talk about pyramids. Right, we all have been hearing about pyramids since we were very young, but in geometry, a pyramid has a very, very technical definition, okay? And it's similar to a prism. So a pyramid, exercise number 3, a pyramid is a solid where one face, known as the base, is a polygon, and all other faces are triangles that meet at a common vertex. So this is cool. You can make all sorts of different pyramids, right? And the idea is kind of simple. You've got some polygon down here. Maybe it's a square. Maybe it's like over here. This thing would be, again, a pentagon. And then there's some point vertically above it. And you would simply take each vertex on the polygon and connect it up to that common point, giving us faces that are then triangles with one face. Could be a triangle down here as well, but one face that's just some type of polygon. All right. Letter A. Explain why the horizontal cross-sections of these pyramids would not be congruent to the base shapes. Is there a special relationship? So before with prisms, when we sliced them horizontally, that cross-section was congruent to the base, but now it won't be. Why not? Well, what's hopefully obvious is that the cross-sections are getting smaller. The cross-sections are getting smaller as you approach, wow. Random red, as you approach the vertex. All right, so as you approach the vertex, the cross sections are getting smaller, also known as the apex of the pyramid, right? The cross sections the cross sections will be similar. So they may not be congruent, but they'll be similar to the base, which is kind of cool. All right. Now, letter B. Under what conditions would the triangular sides of the pyramid all have to be congruent to one another? Because they don't have to be. Again, you can easily have pyramids where those triangular sides, right, that sort of go around the pyramid aren't all the same shape. But sometimes they are. What do you think would be necessary for all those things to have the same shape, to be congruent to each other? Well, there's really two things that are important. First, one, the base would need to be a regular polygon. All right, and two, the apex or vertex, oh, that does not look like apex. Let me try that again. The apex would need to be directly above the center of the regular polygon. And granted, most pyramids, this is sort of what we think of, right? In fact, the two that are pictured right here look like pyramids that fall into this category, where perhaps this is a square, right, a regular quadrilateral, and then immediately above the center of the square is the apex, and so each one of those four triangles are identical. Likewise for this regular pentagon, right, then right above, immediately above the center of the regular pentagon is the apex, and all of those then triangular faces that go around the pyramid are identical. All right, let's look at one final shape that is very similar to a pyramid, and that's a cone, right? So cones, let's take a look. A cone is a shape very similar to a pyramid, except that its base is enclosed by a curve instead of a polygon. So it's kind of like, you know, you have prisms, and then you have cylinders. And cylinders and prisms, very, very similar. Then you've got your pyramids, right, and your cones. And again, same idea. You know, with a cone, you've got some kind of enclosed shape here, right, by a curve. Almost always circular. And when we really kind of get into calculating volumes and things like that, we'll pretty much stay with circular cones. And then right above the center of that cone, the apex of the cone, or right above the center of that circle, the apex of the cone then, you know, kind of comes down to all portions of the circle. All right, so let's take a look. A. Similar to a cylinder, a cone can be produced by rotating a common two-dimensional shape about one of its sides. What shape? And draw it on the cylinder. So remember how we took a rectangle, and we can rotate a rectangle about one of its sides and produce a cylinder. What would we need to rotate in order to produce a cone? Well, we'd have to rotate a triangle. Rotate a triangle, right? And this is how it would look. If we came in and we took a triangle, in this case it would be a right triangle, and again we rotated it about some axis, beautiful looking axis. We took this axis and we started to twirl it, right? Then that triangle would sweep out the cone, right? The space, the three-dimensional space that two-dimensional object would take up as it was twirling around one of its two legs, right, would produce a cone. Granted, if I was rotating it about the actual hypotenuse, it would not produce a cone, right? But certainly rotating a right triangle about one of its legs would produce a cone. Now the cross sections of cones are amazingly important in higher level math. In fact, the cross sections of cones give rise to what are called the conic sections. The conic sections, conic for cone, all right? And they're really quite a variety of them. In fact, the last little portion, what we're going to do is just talk about what we see. So here I've got a cone, and I've got 4 different cross sections of the cone, right? And all I want us to do is kind of describe them. So in this case, what I've done is I've taken the cone and I've sliced it horizontally. And what is that horizontal cross section? Well, it's circular. Or it's a circle, right? If I slice it just like when I was slicing a pyramid, right, then I get a circle up here that's just simply a smaller circle than the one down there. On the other hand, if I slice it, but I kind of don't quite slice it horizontally, I kind of slant my bread knife a little bit like this, it probably still looks kind of circular, but it's not. It's sort of an elongated circle. Or what you will eventually know as an ellipse. All right, so for those of you that have studied a little bit about orbits of planets around the sun, they go in an ellipse, something that looks more like this as opposed to a circle. Now, what about if I slice it vertically? Well, if I slice a cone vertically, as long as I don't slice it vertically through the apex, right, now we get a cross section that kind of looks a little bit parabolic. Right, a little bit parabolic. It's actually, if we slice it perfectly vertically, it's called a hyperbola, but we're going to just say we get a parabola-like cross-section. And what's kind of cool is if we do slice it vertically right through the apex, then our cross-section is a triangle. Right? So if you literally came up to a cone, I took this right circular cone and I just sliced it right through the apex, I would get this triangular cross-section, right, that I would see. So cones are very complicated in terms of what their cross-sections can look like depending on how you slice the cone, right? And cross-sections are important. In fact, if you've ever heard of MRIs or CAT scans, not that they're the same thing, but they're very, very similar. You know, essentially what people are doing is they're looking at cross-sections of the human brain, and they're able to actually put those cross-sections together in order to get a sort of more three-dimensional view of what the brain looks like inside of somebody's head, right? So cross-sections can tell us sort of overall what a three-dimensional object looks like by simply knowing what its two-dimensional cross-sections look like. That's sort of kind of where we're going with today's lesson. There's not a lot that you take out of today in terms of formulas or proofs or things like that. Today is about learning terminology, being able to visualize a little bit in terms of these cross-sections so that in future lessons we can use those ideas as we start to do some calculations. Let's wrap up. So we saw four distinctly different types of solids today. We saw the prism, right? We saw related to the prism, the cylinder. We then saw a pyramid, and related to a pyramid, we saw a cone. All right. Make sure that you can distinguish between these objects in terms of simply their definitions. Know what a prism is. Know what a cone is. Know what a cylinder is. Know what a pyramid is. All right. Because sometimes they'll simply be a description of one of these things, and if you don't know the terminology, it can make it hard to do the problem. All right, but you'll get a little bit of practice on that on the homework. For now, I'd like to just thank you for joining me for another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.